All right, let's talk about AI. We're going to cut through all the jargon, all the hype, and get right down to what you really want to know. How does this stuff actually work? We're going to build one together from A to Z, right here, right now. So let's get into it.
I mean, you've probably seen it, right? An AI spits out this mind-blowing piece of art, or writes code that actually works, and you're just left there thinking, how? It seriously feels like magic, doesn't it? But what is really going on under the hood?
Well, here's the secret. It's not magic, not even close. It's a system. And believe it or not, its whole design is inspired by the most complex, most amazing thing we know of, our own brains. And that's our plan for this explainer. We're going to build one step by step, so you can see exactly how all the pieces click together.
Okay, first things first. Before we can start laying any bricks, we gotta know what kind of house we're building, right? So what's the actual goal here? What does it even mean to simulate intelligence?
This question really gets to the heart of it. If we want a machine to think, what does that actually involve? It's about so much more than just being a fancy calculator. We're talking about replicating the very core abilities that our brains use every single second.
And it turns out the experts have kind of boiled it down to these 5 fundamental pillars. For an AI to be considered intelligent, it needs to be able to do all of these things. It has to learn from data. It needs to reason to connect the dots. It has to be able to solve problems. It needs to perceive the world through things like images and sound, and it has to get a handle on language. Get these 5 down and you're on your way.
All right, so we've got our blueprint. Now let's grab our magnifying glass and zoom way in. We're going down to the most basic, the most fundamental Lego brick of our artificial brain, the artificial neuron.
You can see the parallel right here, and it's pretty incredible. A neuron in your brain gets a bunch of signals, thinks about them for a split second, and then decides whether to fire off its own message. Well, an artificial neuron does the exact same thing, just with numbers instead of chemicals. It's basically a tiny, math-based gatekeeper. So how does this little gatekeeper decide what's important enough to pass on? That's where 2 key ideas come in: weights and bias. Think of a weight as a volume knob on the connection from another neuron. If the signal is super important, you turn that weight way up. If it's not, you turn it down. And the bias, that's like a little nudge that makes it easier or harder for the neuron to fire. These are the tuning knobs the AI is going to learn to adjust all by itself.
So one neuron on its own is honestly kind of simple, but the real power, the real magic happens when you connect thousands or millions of them together in a huge layered structure.
Yeah, think about it like this. A single neuron might be able to tell if one tiny pixel in an image is bright or dark. That's a super simple decision. But what happens when you get a whole army of them, all talking to each other, passing messages back and forth?
What you get is a neural network. This is the brain we've been talking about. By arranging these simple neurons into layers, they start to work together as a team. And that team can suddenly go from seeing one pixel to recognizing incredibly complex patterns, like spotting the difference between a cat and a dog in a photo.
This quote just nails it. The entire setup is directly copying biology. The artificial neurons are like our brain cells, and the connections between them, the edges, they're just modeling the synapses that let our own neurons communicate. It's a bio-inspired design.
Okay, we've built the structure. We have our network of neurons all connected. But there's a problem. It's a complete blank slate. It's an empty brain. So how does it actually learn anything? This is the engine room of the whole operation.
Believe it or not, learning for an AI starts with being wrong, over and over again. Every time the network makes a prediction, we use something called a loss function to calculate an error score. It's just a number that tells the AI exactly how wrong it was. The entire goal of training is just to get that error score as close to 0 as humanly, or I guess artificially, possible.
So how does the AI lower that score? It can't just study harder, that's the job of the optimizer. You can literally think of it as the AI's personal coach. The optimizer looks at the error score, sees it was bad, and then goes back into the network and starts methodically tweaking all those little tuning knobs, the weights and biases, to guide the network toward a better answer next time. It's the engine that drives improvement.
And just like with real coaches, there are different coaching styles. You've got some, like one called SGD, that takes small, steady steps. It gets the job done. But then you have more modern, adaptive coaches, like one called Adam. Adam is smart. It knows when to make big, bold changes because the network is way off, and when to make tiny, careful adjustments as it gets closer to the right answer. And as you can see here, that smarter coaching style helps Adam get to a higher accuracy. It's why it's a go-to choice for a ton of developers.
Okay, so we've built our network, and we've coached it to make incredibly accurate predictions. We're done, right? Mission accomplished? Well, not so fast, because now we run into one of the biggest and most important challenges in the entire field of AI. It's known as the black box problem. See, some simple AIs are like a white box. You can look inside and clearly see the logic behind a decision. But the most powerful, deep neural networks, they're a black box. They give us the right answer, which is amazing, but the web of calculations inside is so unbelievably complex that even the people who designed it can't always explain how it got there. And that's where this whole field of explainable AI, or XAI, comes into play. It is a massive effort by researchers around the world to create tools and techniques to crack open that black box, to translate the AI's bizarre internal math into reasoning that you and I can actually understand and trust. And this isn't just some academic curiosity. This stuff matters a lot. We're using AI for huge, life-altering decisions. If an AI diagnoses a patient with cancer, the doctor needs to know why. If an AI denies you a loan for a house, you deserve a reason. In fields like medicine, law, and defense, getting the right answer simply isn't good enough. We have to be able to trust how it got there.
This quote just says it all. If we, as humans, are going to work effectively with AI in the future, that partnership has to be built on a foundation of trust. And you know what? You can't trust what you don't understand. Transparency is everything.
So there you have it. We have gone on a full journey here, from the smallest possible building block, that single artificial neuron, all the way to assembling a full network, coaching it so it can learn, and finally, confronting the massive challenge of making sure its intelligence is understandable to us.
And that brings us to the final, crucial question I want to leave you with. As these AI systems get more and more powerful and woven deeper into the fabric of our lives, we all have to decide what we value more. Is it enough for an AI to just be right? Or do we need to demand that it's also understandable? The answer to that question is going to shape our entire future with this incredible technology.